Hello everyone, and I'm Stefano Cariddi from Ennova-Research, senior researcher, and we are here to talk about unstructured PDF ingestion for processing. Before starting, just a couple of things about the company, because we work there, so it's, I think, nice to share about the company with you. We are a company with 8 locations throughout Italy, like 150 researchers work here. We are active in AI, data, ML, cloud, industry 4.0, IoT, CXM, web development, a lot of things. And one of the nicest things is that like 14% of the revenue go to research and development, thanks to which we can develop and actively research cool stuff like the ones that we are going to see today. So I think that this deserves to be mentioned. Now, let's go to the topic. So, as I said, automatic unstructured PDF ingestion for question answering with state-of-the-art document segmentation modules and Google OCR. So, I would like to actually start from... so we live in a moment where LLMs are in the mouth of everyone. And I would like to start addressing the elephant in the room, let's say, because not all LLMs are capable of knowing real-time information. There are LLMs like Bard, or like the new LLM that is being developed by Elon Musk, that are capable to. But this is not, let's say, the standard. A model needs to be trained on some data, which means that data need to be gathered at a specific moment in time. So ChatGPT, I'm mentioning it because it's probably the best one that is available right now. It's a great example of a model. It is very powerful and it's not updated. It does not know what's happening today around the world. So the question is, how do you succeed in creating a model that is aware of a custom amount of information? It could be live data, it could be a specific database from your company. So how can you do it? This is what we're going to see, to address now. And in this context, let's just focus on PDF, because there are many ways of gathering data. PDF are one of the most common ones, okay? And the big problem with PDF is that they are unstructured. So basically, you have a tree of elements inside of it, inside of a PDF, which are not really organized like you could expect from an HTML, a Markdown, something like this. So it's not obvious to just give it to a model and tell the model, okay, just make sense out of this. It's absolutely not obvious. You need to have an entire pipeline that does this. So we start from a PDF, and we need to perform test segmentation. That's the core of it. We need to segment the PDF, which is this step, and to transform it into a structured format. Here we put HTML, but it could be anything else, as I said, and to store the information on a vector store, on a vector database. We will see about these later also. Just 2 words about them for context, since I mentioned it. A vector store is a kind of database that saves information in vectors, really. So you can ask a question, which will be transformed into a vector, and it will give you an answer, which will be the closest vector to the question that you asked. So the question arrives and from the user. It could be, let's assume that we are going to, do some custom project for, I don't know, the public administration. The question could be, which is the date of the payment for this contract? It goes inside the vector store, and the vector store fetches the amount of information that are closest to the question, and it passes them to a large language model. So the large language models reads them, evaluates them, and returns an answer to the user. This is what it's called a RAG, which means retrieval augmented generation. This is one of the most powerful things that we have right now. Google, actually, I'm mentioning this because as a company, we are Google partners, okay, has a super cool instrument, which is called Vertex AI Search and Conversation. that specifically does this automatically with a click. So you just upload the document and the magic is done. So probably you're wondering, okay, so if they do it, why are you even here listening to you? Because this is a super cool tool that is absolutely general. So it's great for having a baseline of performance and for having a very quick application. You can just upload it and check the performance that you can achieve. But of course, clearly, it's not specific. So for specific use cases, it could be that maybe it fails because the format of the data is not does not allow it to retrieve the information precisely. It could be that in some cases you need to customize stuff to add metadata to what you're doing. So as a baseline tool, it's awesome. But if you want to actually move the bar to a higher level, what you need to do is something more use-specific. And this is what we are going to see right now from now on with Ivano, who will lead us to all the details for this specific procedure. Maybe we have a so that I can get closer. Oh, great.
So, as Stefano said, I'm Ivano. I am an AI engineer at Ennova-Research. And yes, Stefano already introduced the problem. So, we have a PDF document that contains layout information, the design information, along with the text, but does not contain any semantic information. So, saying which text is the title, which text is a table or a list or a paragraph or so on. And this is not ideal for an LLM, which expects structured text. The more structured information you can give, the easier its job is. So what we want to do is to transform this unstructured document into a structured document, such as HTML or Markdown, just to name a few. There are three main problems in this process. The first is inferring the semantic structure, so understanding the semantic label of each component in a page, defining the reading order, so the layout, understanding, in our document, usually we go from left to right, top to bottom, but for example, even simply a two-column page, this assumption is not real anymore. We need to read from left to right, top to bottom, but one column at a time. And then, when we know the reading order of each semantic element in the page, we need to associate a text with it. And so we go through all three. So for the first step, there are a lot of models that perform specifically document segmentation and semantic labeling. Specifically, they are mostly computer vision problems. So they look at a PDF page as an image, a rendered image, and they retrieve bounding boxes and semantic labels for these boxes in the page. As I said, for example, these are some semantic labels. So the picture, a table, the heading of a section, and knowing the specific label is essential to understand the text, where it goes and what does it mean and which context does a single block of text have. This is an example of what you can get with a state-of-the-art document segmentation model. You see there is the text and a bounding box surrounding each element. In case you're looking at implementing something like this, just a word of warning: when you are working with pre-trained document segmentation models, either you are working with documents that are very, very close to the training set, otherwise you will not get the best performance out of these models. There can be some random errors, like if you look at the bottom left, we have the segmentation of the page and the retrieved bounding boxes, which are much larger than the actual segment of text because there are random single pixels activated around the image with the same label. And so very easily, if you are familiar with computer vision, you can perform some morphological tasks, operation on the image to remove these random pixels when they are not part of a big blob of activated pixels around the same position to get bounding boxes that do not include other text or are very tightly fitting around the box of text that you are considering. Now, as I said, we need to find the layout, and this is very, very custom. This depends on the client, this depends on the designer that makes the PDFs. I would say that the most generic case is a single column or double column, and this is quite easily done by just checking the white space between the elements. We have bounding boxes around the image. You have a big bounding box, which is the dimension of the whole page, and you can check for gaps between bounding boxes to define a standard layout. And for custom purposes, you have to implement a custom layout extractor. Okay. The last point about ingesting a PDF file is defining which text goes in which bounding box. There are some state-of-the-art models that perform these tasks along with the segmentation. This task specifically is called usually OCR, so optical character recognition. But for our model of choice, this was not a feature of this model. And so we need an additional step to perform OCR on the page. Since we are Google partners, we like to use Google, and so we use two models available on Document AI, which is a Google OCR processor, which extracts text from images, and the Google Font processor that is better suited for extracting key value pairs like forms, like in this case, or classical tables. In our case, using Google tools allowed us to achieve a better performance than with just the state-of-the-art segmentation model, because our model only has the table tag, does not have a table cell or table row tag or a form tag, which Google does. And so by linking the result of the state-of-the-art segmentation model and the Google Form parser, we are able to distinguish between cells in the table, and we are able to distinguish between forms and tables, so enriching our result. If you perform all these steps, then the rest is easy. Rendering to Markdown, HTML, or whatever other Markdown language you want to use, just simply needs to prepend and append at the end the language tags. So if you have a title, HTML, you put the text of the title before you put h1, at the end you put /h1, and you are done with the render. So if you performed all the previous steps correctly, then the choice of the rendering language depends on your use case. You should try and try again and see which language your LLM understands the best. Okay. There are still some issues with both Google tools and our implementation. For example, in this case, there is a case of bad design, in my opinion. There is a form, so a list of key value pairs, but the white space between key and value is not consistent. And in some cases, the value goes over the key. And so our model does not understand that this is a table or a form, and so it labels it as text, plain text. And also Google cannot recognize it fully as a form. You see, it sees everything as text, but the first four components of the list of the key value pairs are separated well enough to be classified as a separate component. And rendering these results in text that does not follow the original order and completely changes the significance of the text. So yeah, you should be aware of these kind of situations and perform custom fixes for these kind of problems. Perhaps asking the designer to allow a bit more space for this form. Okay, so now we have a rendered HTML or Markdown document, and we want to understand how we can use it inside an LLM to perform question answering. And as Stefano introduced before, we use vector stores. In this case, we use a function called an embedder, which its function is to transform a string of text into a sequence of numbers, so a vector, and to be able to perform like distance calculations or additions or means and so on. So usually a string of text representing a document is broken into tokens, which can be words or part of words. And each of these tokens is transformed by an embedding function into a vector. And all the vectors obtained by a single document are stored in a classic database, which in this case is called the vector store because it contains vector. And what happens when the user asks a question? You take the question, you split it in tokens like you did the document, you perform the embedding and search for the closest vectors in your database. And a particular thing about embedding functions is that the distance between two vectors is related to their similarity. So the lesser the distance between two vectors is, the more similar their meaning in the training set of the embedder is. And so by retrieving the closest instances in the vector store to the user query, we can find the snippets of text that are more likely to contain an answer to the question. So it's really critical to choose what we want to save in the vector store, because we can, when you have a text that is longer than one token, it still gets transformed into a single vector. And usually what is done is that all tokens are transformed into vectors, and then a mean of the vectors is performed. So you have an average meaning of the text. And so the smaller elements you put in the vector store, the closer you are to the original meaning. The longer text you put, the more the meaning gets diluted with all the other words. But you get also a bigger or smaller database depending on your choice, and the choice of how you divide your text should be done according to the client needs and according to the quality of the results that you get. In our case, we chose usually to embed atomic elements. So for example, for tables, we embed each cell separately, or for lists, we embed each item separately to get the smallest amount of context that we need to have a good embedding. Now, when if you get a user query, as I said before, you transform it into a vector and you look for the closest matches in the vector store. And we said that in the vector store, we store atomic elements with very little context. And so to get better answers from our question answering system, what we do is start from the retrieved element and backtrack to the smallest section containing it. So we have the minimal amount of context that allows us to contextualize this element that we retrieve to the question answering bot. And now the final step is to write your own prompt for ChatGPT, for Pan2, for whatever LLM you choose to use. And it's very important that you include instruction in your prompt that tell the system to only use knowledge from the passages that you extracted. So you get all your relevant information from the vector store, and you write a prompt that says like, here's the user question, here is a set of information that should contain the answer. Please write an answer only using the information that I provided you. Of course, this is a very, very simple prompt, but you can start from there and try and see what works. But if you don't specify that you want the information from the prompt, it can happen that the model uses its own information that it learned from this training set. So if your task is generic, you have to be very careful because it might know something already, and it might want to answer from the knowledge that it already has. Okay, that's the end, and we close with the future prospects. For now, we talked about textual documents, textual information, strings, but right now there are some models being developed that allow us to create a vector store embedding both strings and multimedia data using the same embedder. So they end up in the same vector space, and with a retrieval from the vector store, you can get either a snippet of text or an image that closely resembles the user query. Or the user query can be an image, and you get in output a string of text describing it in the vector store. And for now, for example, in our models, we discard images because we cannot process them. But using an embedder of this kind would allow us to also include schemes present in the documents that right now we cannot access. Okay, here are our contact information, and this is the end of the presentation. If you have any questions, we are here. Otherwise, thank you.